We tend to think of time as a universal background track, a master clock ticking away at the exact same rate for everyone, everywhere. But time is actually a highly personal, flexible experience. In October 1971, physicists J.C. Haffel and Richard Keating booked seats on regularly scheduled, ordinary commercial airline flights going around the world. They brought along 4 highly precise cesium atomic clocks. They left a matching set of clocks ticking on the ground and took their 4 clocks into the air, flying eastward and then westward across the globe. When they landed and compared their travel clocks to the stationary reference clocks at the U.S. Naval Observatory, the times no longer matched. The flying clocks had recorded fewer nanoseconds passing compared to the clocks that stayed home. This confirmed an idea that physicist Paul Langevin had proposed as early as 1911, using basic elements.
Langevin pointed out that if you sent a sample of radioactive radium on a high-speed round trip, it would undergo less decay than an identical piece of radium left sitting in a lab. From mechanical ticks to decaying atoms, the physical evidence is consistent. Moving through space slows your progression through time. Scaling those fractions of a second up to human lifespans reveals a startling reality. Imagine it is the year 2200, and we send an astronaut toward a deep space nebula. Our astronaut has a twin sister who stays behind. He boards a ship, accelerates to 99.9999% the speed of light, travels out for 1 year of his own time, and then spends 1 year flying back. From his perspective inside the cabin, exactly 2 years have passed. He steps off the ship biologically 2 years older than the day he left. But the world he knew has vanished. Because of the speed he traveled, roughly 1,414 years have ticked by on Earth. He lands in the year 3644. Here, we hit a logic trap born from the fact that motion is relative. From the astronaut's perspective looking out the window, his ship was perfectly still, and the Earth was the object flying away from him at light speed. If both twins can claim that the other person was the one moving, why does the astronaut stay young while his sister ages by over 1,000 years? In special relativity, velocity depends on your perspective. Without an absolute state of rest, motion is just a matter of how you define your coordinates. From the Earth twins' point of view, the ship moves at extreme velocity, meaning her brother's clock ticks slower. But sitting in the ship, the brother feels completely stationary. He sees Earth flying away, expecting the Earth's clock to run slower. Both descriptions are valid within the rules of relativity. Each twin has the mathematical right to expect the other to be younger. This creates a contradiction that requires a structural tiebreaker. For one twin to actually be younger at the reunion, one of them must have a unique physical experience that the other does not. Special relativity alone cannot resolve this standoff. We must look for a specific physical anomaly that shatters this symmetry. The traveling twin performs one unavoidable action that the Earth twin does not. He turns around. To come home, the ship must abruptly decelerate, stop, and accelerate back toward Earth. This creates significant structural vibration and intense physical forces inside. Physics defines an inertial reference frame as a state of smooth, constant motion where no physical forces are felt by the observer. Earth remains in one constant inertial frame for the entire trip. The ship, however, must transition through 3 different states: moving away, the turnaround, and the flight back. The massive G-forces felt during that turnaround prove the ship is the object genuinely moving. While the sister on Earth feels nothing, the astronaut is physically crushed into his seat by the change in velocity. This physical force is what breaks the symmetry. The act of accelerating to turn back is what causes the traveler's clock to permanently slow down. When the twins finally reunite, they find a stark biological contrast. The astronaut is still in his prime, while his sister has long since passed away from old age. The resulting age difference is a permanent physical change. It is the same effect we verify every time we synchronize high-precision atomic clocks on the ground and in orbit. The universe lacks a master clock. There is no universal now that applies to everyone. Instead, time bends and stretches around the specific path an individual takes through space. Controlling your personal time provides a gateway to the deep future. But that leap comes with a permanent consequence. By the time you arrive, the world you left